Our second unit in Semester 2 Physics is called Magnetism and Electricity. The topic for today is magnets, and this is going to be part 1 of magnets. This is going to be due for odd periods on Monday 2-24, February 24th. Even periods, this is due on Tuesday, February 25th. Hopefully you're pretty familiar with magnets. For example, if you think about on your refrigerator, you've got magnets that are holding up all of your beautiful paintings. However, there are many other areas of life in which we use magnets. For example, credit cards. The little black strip on the back of your credit card, that's actually magnetic. So if you were to actually rub a magnet along this strip, what would end up happening is you'd actually ruin the card. TVs and computers also have magnets in them. So for kind of the similar reason, if you were to bring a magnet close to a computer, you'll end up seeing the screen go all kind of wonky colors. So don't do that. For the same reason you shouldn't put a magnet across the credit card. Cars use magnets as well. They use them for their motors. They use them as well for their automatic windows and even for their windshield wipers. Another common use of magnets is in compasses. Never eat soggy waffles. Yeah, in compasses, remember, because of the magnet, it always points north. And we'll kind of get to see that in class. So magnets have a huge number of uses, even some unexpected uses. And we're probably pretty thankful for most of these things. The magnets that you're familiar with are probably some type of iron or steel that can attract certain metals. Magnets always have what we call a north pole, and they also have a south pole, and they'll always have those two poles. When we have two magnets, it's important to understand that opposite poles, right, so opposite poles, for example, here's north, here's south, if I put those two poles next to each other, they will attract, all right? So opposite poles always attract. If I have two poles that are exactly the same, what we call like poles, such as north and north, when I put these two together, they actually will repel from each other. Repel meaning they'll push away from each other. So for example, if I try to bring these close together, what will happen is they will push apart. They will not want to be next to each other. This is the same as if, for example, I were to do south and south. Because these are like poles, they're the same type of pole. If I move them together, they will repel apart from each other. Another cool thing about magnets is that if we bring these opposite ends together, opposite poles, and they attract, what kind of happens is that two magnets is going to be better than one. So when I bring these together, they'll stick together and essentially make what is a bigger magnet. So it essentially becomes something like this, where I still, because if we look before, I still have, I still have over here on the left part north, and on the right part I have south. And so when I stick these together, essentially those ends take over. So if I go up here, I'll end up with north over here and south over here. And so it's a bigger, better, stronger magnet. Similarly, if I go ahead and I cut this into 4 different pieces, you would think that you might end up with 2 north sides and then 2 south sides. But the reality is that no matter how many times you cut a magnet, it's still going to always have 2 poles. So when I cut this into 4 different pieces, I actually end up with 4 smaller, weaker magnets. So I'll end up with 4 magnets like this, each of which had their own north-south, 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 north-south sides. Keep in mind that because the north over in this case was on the left, my north will continue to be on the left side of the small magnets. In the same way, since my south was on the right, my south side will continue to be on the right side of the magnet. All magnets have what is called a magnetic field. And the magnetic field is an invisible region around the magnet where it can actually affect other materials. Lines go from the North Pole, you can kind of see here they're going from the North Pole down to the South Pole. Lines never overlap, they always have to be pointing towards the south. Near the sides of the magnet you can kind of see how they're going straight from the north to the south side. As you imagine, we get further and further out, this kind of becomes bigger and bigger, regions like this, until at some point, for example, from the north, straight out from the North Pole, we have an arrow pointing outwards, and straight into the South Pole we have an arrow pointing inwards. We learn more about the math behind magnetic fields later, but just know for now that we label the strength of a magnetic field with the letter B with an arrow, which means that it's a vector. And remember, vectors have direction. The units for the magnetic field strength is called the Tesla, so Tesla, which we label with a T. So for example, a very strong magnet could have a, I'll write this in a different color, could have a magnetic field strength of B equals 4.0 Teslas, or it could have a very, very weak magnetic strength, such as a refrigerator magnet with B equaling 0.005 Teslas. If we look at the magnetic fields of two magnets interacting, we can see how the lines go between the north and the south poles of the magnets. So for example, if we look at our opposite poles, we can go ahead and we can see here how the north lines are going towards the south pole. Sorry, the lines from the north pole are going towards the south pole of the other magnet, which is why at this point right here we have such a strong attraction, because we know opposite poles attract. On the other hand, if we look at two like magnets, or two like poles interacting with each other, let's say for example north and north, the magnetic field lines actually move away from each other. So you can see how they're starting off towards each other, but then they actually move away. So instead of going from north to north, the magnets just go from their north poles over back to their south poles, which kind of leaves an area right here where there is no magnetism. So this is showing how magnets will actually repel from each other. Remember that the magnetic field shows us the places where a magnet can actually affect other materials. However, only some materials can actually be affected by magnets. So magnetic materials are materials that can be attracted to magnets and can even sometimes become magnetized themselves. There's a really easy way to remember which ones are magnetic, and we call it coins. So C-O, capital I, capital N, capital S, coins. So the materials are, CO stands for cobalt, the I stands for iron, the N stands for nickel, and the S stands for steel. So all of these materials are magnetic. They're attracted to magnets and they can actually become magnetic themselves. Materials that don't attract magnets are called non-magnetic materials. And example of non-magnetic or mostly non-magnetic substances are lead, zinc, copper, aluminum, so for example foil is not magnetic, tin, so your cans generally aren't magnetic, gold, silver. Some things that aren't metals that are non-magnetic are wood, plastic, glass, and for the most part water. These things tend to be non-magnetic. That's it for today. Make sure you take good notes on page 3 of your booklet, and you are ready for your quiz tomorrow. See you later. Bye.